We're here to discuss the action potential and the resting potential. And on the left here, I've got the keywords that we should be looking to use in an exam answer. And I've also got a graph of an action potential, and we have time on the x-axis, and we have volts in millivolts on the y-axis. And what I'm going to do is I'm going to talk us through, first of all, how we gain a resting potential, and then I'm going to talk about the action potential. Now, let's introduce the cast. We've got an axon plasma membrane. It's actually called an axolemma, technically, but it's a membrane like many others you've met. You've got the phospholipids, and then you've got these proteins. And there's 4 proteins that I'd like us to learn about. There's number 1, number 2, number 3, and number 4. And these are responsible for manipulating, certainly to start with, the ion concentrations across each side of the membrane. Because if we're able to manipulate those, then if we allow them to fall down their concentration gradients, for example, or keyword electrochemical gradients, then we are going to allow a movement of ions which can be used as a signal. And neurons carry electrical signals. So the reason why they're electrical is it's the movement of charged particles. Now you know from electricity that electrons are negatively charged, and so electricity is the movement of charged particles that happen to be negative. But electrical can actually be the movement of any charged particles. And in this case, the key players are sodium, Na+, and potassium, K+. They are plus ions because the atoms themselves have lost an electron, and so there's now more protons in the nucleus than there are electrons, and therefore they are slightly positively charged. Now, in a cell, you have lots of these ions, billions and billions and billions in fact. And what the nerve cell is going to do is manipulate the movement of these 2 ions in particular to create a scenario that it wants. And the scenario is that it has loads of the Na pluses outside the cell membrane. And lots of K pluses inside. Now the way it does this is this protein number 1. This is a sodium-potassium ATPase. And that means using ATP, it pumps, obviously it's an energy source, it pumps sodiums out of the cell. In fact, it pumps 3 Na pluses out. And it pumps 2 K pluses in. Now, this is going to mean that there's more sodiums on the outside than on the inside. But there's a couple of subtleties that we need to appreciate here. The first is that 3 pluses are pumped out to 2 pluses coming in. So the outside is going to be more positive than the inside. The other thing to say is that there's loads of sodiums out here and not many here. So there is a concentration gradient here, sodium high, sodium low, and a concentration gradient here for potassium, potassium high, potassium low. So we've actually got a concentration gradient for each of these ions. And, as we're going to see in a minute, a second gradient based upon the plus charges, which is called an electrochemical gradient. So after this ATPase, this sodium-potassium ATPase, has done its work, it's going to create a scenario where there are now loads of sodiums on the outside, loads of potassiums on the inside, not so many sodiums on the inside, not so many potassiums on the outside. Now that forms a bit of an electrochemical gradient, because if the ratio is 3 to 2, plus ions being ejected and pumped in, then the relative, and this is an important word here, the relative charges of outside and inside the membrane are going to be different. And this is going to be more positive than this. So if you were to take the numbers plus 100 and plus 20, plus 100 is more positive than plus 20, and therefore by extension plus 20 is more negative, closer to minus 1 than plus 100 is. And so we can say that this is more positive, but this is more negative. And we call this difference in positivity a potential difference, like a gravitational potential difference of somebody being at a different height. There is an electrical potential difference because there are more pluses here than here. But when we talk about this potential difference, we don't talk of it in terms of plus 100, plus 20. We actually make this outside 0. And so if you made plus 100 your 0, plus 20 would be something like minus 80. And this is exactly what we do. We say here that the potential difference between these, the outer and inner, has a negative value. And I'm about to tell you what that is. Minus. The sodium-potassium pump on its own is capable of creating this discrepancy between numbers of pluses here and non-pluses here. But actually, they're not that different. There is another important protein in the membrane that allows the difference in charge between these two to increase to a key value of minus 70 millivolts. And this is the potassium leak channel. And what this does is, you can see here there's a channel that goes straight through. It's always open, always open. You're going to see that some of the proteins in this process change and are closed and opened or inactive. But this leak channel is always open. And this comes back to the importance of what I was saying earlier about the two types of gradient that exist. We've got the concentration gradient of the actual ions themselves, high sodium, high potassium, low potassium. And we've got the electrochemical gradient of more positivity out here, less positivity in here. And we actually have created, as I said, not that big a difference in charge between these 3 pluses going out and 2 pluses coming in. So there is a gradient, but it's not that steep right now. But there is a very, very steep concentration gradient between potassium on the inside and potassium on the outside. And therefore, the potassiums are allowed to passively leak out of the membrane down their concentration gradient. Sodiums would do the same, be under no illusion about that, but there's no protein that allows them to do that. And because they're charged, the membrane is impermeable to them. And so therefore the sodiums can't go down their concentration gradient. Now, the key is, why do we get to minus 70? Well, by more pluses going out, we now have a situation where there were more pluses outside and less pluses on the inside, we've now got even more pluses on the outside and less pluses on the inside because the potassiums have leaked out down their concentration gradient. And this leads to an overall figure of minus 70. But it stays at minus 70. And I'd like, if I may, to try and explain to you why this happens. To start with, we've got a slight electrochemical gradient here, without the potassiums having gone out, but a huge concentration gradient. So, down the concentration gradient, which is way overpowers the electrochemical gradient, the potassiums start leaking out. There's going to get to a point here where it becomes so positive that potassiums here, looking to go down their concentration gradient, actually are repelled. Because this is now really positive, and these are positive. So like charges repel. And so the point at which we've increased the electrochemical gradient of pluses to pluses is such that it overpowers the concentration gradient, is the point at which we reach a kind of balance. So the potassiums at the beginning leaked out because they were going down a much stronger concentration gradient than electrochemical gradient, but as they've leaked out, there has been a balancing of the concentration gradient versus the electrochemical gradient. The concentration gradient which has been reduced because the potassium's gone out, and the electrochemical gradient that has been increased because we've now got a bigger discrepancy between the pluses on the outside and inside. And that difference between the outside and the inside is called the resting potential. We say that the membrane is polarised. The Earth's poles are at different ends, and if you have an opinion which is polarised between two people, it means they're completely different. And polarised means that we have got a relative plus on the outside and minus on the inside. Remember though, that in truth, this actually might still be a bit positive, but it's relative to the outside, which is hugely positive as a result of our sodium and potassiums that have been manipulated or leaked out. Last thing to say about this resting potential is that there are a few other players in this, and that is on the inside of the membrane are some big clunky proteins which carry a lot of negative charge, and therefore they also add to the negativity of the inside of the axon. They're very big, they can't pass through the membrane, and so they are stuck there, adding, and we call negatively charged particles anions. They add anions to this inside to assist with this minus 70 millivolts. And so there we have the way that the resting potential is achieved. Sodium-potassium pumps create this sodium on the outside, potassium on the inside with a ratio of 3:2. That produces a small electrochemical gradient, but the big changes come from the potassium leak channel allowing potassium to go down their concentration gradient, and that slowly increases the electrochemical gradient to a point at which the potassium are no longer able to go out, even though they want to still, and the balance comes in with the anions included on the inside to a resting potential of about minus 70 millivolts. Keywords, resting potential, and this is now polarised, and I could have included there potential difference, which is the difference in voltage between the outside relative to the inside, which is minus 70 millivolts. And if we look at our graph, this is our resting potential at point A, minus 70 millivolts. Notice that for the resting potential, proteins 3 and 4 are not used at all. We are really achieving this resting potential by the pump and the potassium leak channels.